This lesson is part 3 of galvanic cells. So we're going to take another look at a reaction that we've looked at before. So this one needs to be carried out in an acidic solution. So we have the iron Roman numeral 2 ion that comes from some iron Roman numeral 2 nitrate or chloride or something. And then MnO4 minus, usually from potassium permanganate. And then that reacts to give us the iron Roman numeral 3 ion and the manganese 2 plus ion. So the iron ion goes from 2 plus to 3 plus. It's going up the number line. It's getting more positive, so it is being oxidized. So our half reaction equation, Fe2 plus aqueous yields Fe3 plus aqueous plus 1 electron. The MnO4 minus, the oxidation state of the manganese, is plus 7. That goes from plus 7 to plus 2 down the number line. That is reduction. So we have MnO4 minus plus 5 electrons, gives us the Mn2 plus. But then we have to take care of the oxygens. We have water available, so we put in 4 H2Os. That gives us 8 hydrogens. So then we must put an 8H plus, and we have these H plus available in the solution because our solution is acidic. We have to have our electron balance. The number of electrons lost has to equal the number of electrons gained. So we have to multiply all of our coefficients by 5. Now we can add up our equations and the electrons cancel out. And we end up with 8H plus 5 Fe2 plus MnO4 minus yields 5 Fe3 plus Mn2 plus 4H2O. To get the E0 for the cell, the E0 for the reduction, this value is not on your standard reduction potential chart. I got this out of your textbook in the chapter on electrochemistry, and we have 1.51 volts. For the oxidation, so I did get this value from the chart. So we have Fe, let's see, we're going the other way. This way we have Fe2 plus going to Fe3 plus an electron. Remember the oxidation we have to flip because this chart is in terms of reduction potential. So we flip the equation to match our half reaction. We have to flip the sign of our E0. So we get a negative 0.77 volts. Add them up, and the E0 of the cell is positive 0.74 volts. When the E0 is positive, the delta G is negative. So this reaction is spontaneous as written. So we want to harness the power of this. That negative delta G means there is available work. And so we need to do a cell, but this one is different from the ones we have done previously. We don't have any solids here, so what are we going to use for our electrodes? All right, so let's set up our cells first. So we have our 2 compartments, and let's put in our salt bridge. And this time, maybe we'll put in potassium chloride in our salt bridge. We need electrodes for our cell. And that's going to carry our current. And this, we have some kind of voltmeter here, or a light bulb, or some kind of electrical device. And then we have our solutions. All right, so we'll make this side the oxidation side. So we'll make this our anode. All right, so for oxidation, we have Fe2 plus and Fe3 plus. So for a standard state cell, we need both of these to be 1 molar. So we need 1 molar FeNO3, 2, and we need some 1 molar FeNO3, 3. So we have iron plus 2 and iron plus 3 in our compartment. In this reaction, the ion gives up an electron and becomes it's still an ion. So we need a platinum, PT. Our electrode is platinum, and we use that because platinum itself is very non-reactive. Platinum is called a noble metal because it is very unreactive. So what is going to happen here is that an Fe2 plus is going to come up to the platinum electrode, give up its electron, and then come off as an Fe3 plus. So the platinum provides a surface for the electron transfer. So the electron comes out, goes through our wire from the anode, where oxidation takes place, to the cathode, where our reduction takes place. So for our reduction half reaction, we have H plus, MnO4 minus, Mn2 plus, and water. But water is in our solution. We don't have to worry about the water. So again, we have an ion reducing to an ion. So we're going to need another platinum electrode. So our electron comes through our platinum electrode. And what do we need in this compartment? Well, it's standard, so we need 1 molar for all our solutions. So we're going to need 1 molar, maybe HCl, to provide the H+. We're going to need 1 molar KMnO4 to provide the MnO4, and 1 molar, let's see, MnNO3 too. We need all of these in our beaker. So the MnO4 minus is going to come up to our platinum electrode, has to take 5 electrons. We need the H pluses, all that involved, and then it's going to come off as an Mn2 plus ion. So this is the setup that we need whenever we don't have solids appearing in our oxidation or reduction half reactions. We use platinum. Okay, our next topic is the standard hydrogen electrode, which is abbreviated as SHE, the SHE. And we're going to see that the values that are on our standard reduction potential chart come from comparing our half reaction to the half reaction of the hydrogen. So our standard reduction potentials are determined relative to this standard hydrogen electrode. So let's go look on our paper, our reduction potentials. And right here, this is our value of 0. This has been defined to be 0. So anything above hydrogen has a greater reduction potential than hydrogen. Anything below has a less reduction potential than hydrogen. All right, so we can write this for oxidation or reduction. So we can say that 2H plus 2 electrons gives us H2 gas. And this is a reduction. The hydrogen ions are going from plus to 0 down the number line. And so we can say our E0 of the reduction is equal to 0.00 volts. If we flip this, we get H2 gas goes to 2H plus, aqueous, plus 2 electrons. And the E0 of this oxidation is the same, 0.00 volts. So let's take a look at what we need for this standard hydrogen electrode. So the electrode itself kind of looks like an inverted test tube. And then we have a wire. We got some platinum here. We have some platinum there. Now, we have to have hydrogen gas. For standard state, the hydrogen gas has to be at 1 atmosphere. So we have to pump in some H2 gas at 1 atmosphere. And then if we're in our beaker, our solution, so up here we have hydrogen gas, and in our beaker we have to have 1 molar H plus, so it might be HCl or some other acid. So this right here is our platinum electrode. And then we got the hydrogen gas and hydrogen ions. So let's see how we determine reduction potential using this idea of the standard hydrogen electrode. So we'll look at zinc and the SHE. All right, so here we've got a voltmeter, and this is going to give us the number of volts, and you'll learn about that when you take physics, where you get that. Okay, so we have zinc here, we have our She here, and of course we have H2 gas at 1 atmosphere, and in our beaker we've got 1 molar HCl, or whatever, I'll just put HBr to show a different acid. And over here, so this is our zinc, so we need some 1 molar, and I don't know, I'll use zinc chloride, and we'll put some sodium chloride in our salt bridge. And now we're just going to set up our cell, and it's going to go. And we're going to figure out which of these compartments is the anode compartment and which of these compartments is the cathode compartment. So when this runs, we notice we get a lot of bubbles coming up from our platinum electrode, showing that hydrogen gas is being produced. So we see H2 gas produced. Our pH, as the cell runs, increases, and that is because our H plus is decreasing. So that means we're removing H plus, so we have the 2H plus plus 2 electrons making H2 gas. So we have the reduction occurring, and we can tell by the bubbles and the fact that the pH is changing. So that means that this is our cathode compartment, where we have reduction. And then what would we see happening on this side? So here we notice that the Zn electrode does not get plated. And if we were to measure the mass before and after, we would see that it lost mass. So this is our anode compartment, where we have oxidation. So our zinc is going to Zn 2 plus 2 electrons. And while this is going, so what's happening here with the NaCl? Well, here we're putting Zn 2 plus in the solution, so that means that the chloride ions would come out into the solution. And over here, as we're losing our H plus, we gotta get plus back into the solution, so our sodium ions would come in to maintain electrical neutrality in each of the compartments. We look at our voltmeter and see what it says. That's measuring the E0 of the cell, and it says 0.76 volts. So now, we know that the E0 of the cell is equal to the E0 of the reduction plus the E0 of the oxidation. So our voltmeter tells us our value 0.74 volts, and the E0 of the reduction is 0. The hydrogen is our standard. We define that to be 0, so 0.00 volts plus the E0 of the oxidation. So that means that 0.74 volts is the E0 of the oxidation of the zinc. So now, to get the reduction potential, this is the E0 for this. To get the reduction potential, and that equation would be Zn2 plus 2 electrons going to zinc. We have to take the negative of that. That E0 would equal negative 0.74 volts. And if we look on our chart for zinc, let's see, where is zinc? Where is it? Oh, there it is. There it is. Negative 0.76. Oops, did I put 74? Yeah, I don't know why I wrote 4. That's 6. It said 6 up there. 0.76. That's 0.76. Why did I write 4? I don't know. But that's where this number comes from. We compare the reduction to the standard hydrogen electrode. So we do the same thing for copper and the standard hydrogen electrode. All right, so again, we have H2 gas at 1 atmosphere coming into the, so you need some kind of hydrogen tank that is hooked up to. And then we have 1 molar HCl or whatever, some kind of acid. And now it's got to be hooked up. Our voltmeter connected to our She, connected there. And we have some NaCl in our salt bridge, and we want to see what happens. So as this cell runs, we observe that the pH increases. Oops, is this the right one? No. The pH decreases because the H plus increases. And we don't see all those bubbles coming off of our platinum electrode there. So that means when we have copper, the standard hydrogen electrode is the anode. And we have oxidation. So that equation is H2 gas going to 2H plus 2 electrons. So that means our electrons are coming from the She, going through our voltmeter, and our voltmeter reads 0.34 volts at the initial part of when the battery starts running, the electrocell. So our electrons are leaving the She and coming into the copper electrode. So our copper electrode now is the cathode, where we have reduction. And in here we would have to have some 1 molar copper nitrate or something. All right, so what do we notice as this cell runs? We notice that the copper electrode gets plated. It gains in mass. So if this is gaining in mass, it's because the Cu2 plus ions are taking 2 electrons and plating onto the copper electrode. So now we have the E0 of the cell equals the E0 of the reduction plus the E0 of the oxidation. Our voltmeter gives us 0.34 volts. the E0 of the reduction. That's what we're looking for. And then the E0 of the oxidation, this is always 0.00 by definition. So then we have that the E0 for the reduction, this is the reduction of the copper, is equal to 0.34 volts, because that's the reduction of the copper ion. And that is the value that we see on our chart. Copper plus 2 electrons is positive 0.34. So our E0s will be positive if they have a greater reduction potential than hydrogen, and they'll be negative if they have a less reduction potential than hydrogen. And we can experimentally determine what that is by setting up an experiment with the standard hydrogen electrode. That's it.